Let's solve longest substring without repeating characters by learning about the brute force approach and then converting it into a more optimized version. In this question, we have been given an input string s and we need to find the longest possible substring without any repeating characters in it. So, for example here, ABC is a valid substring because no duplicate characters are present here. But on the other hand, BCB is invalid because B occurs twice in it. One more thing to be noted here is that S can consist of various characters. Hence we need to make a generalized solution for this problem. One way to approach this is by keeping track of all the possible substrings. When we traverse the string, we will keep track of the longest possible valid substring that can be formed starting from the particular index. Once we have all the possible substrings, then we will simply take the longest substring out of all of them and its length would be our final answer. Great, we can find the substrings and their length to get the answer. But how exactly will we check if any duplicate elements are present in those substrings? For that purpose, we will use something called as a hash set. Sets are very closely related to hash maps, with the difference being that in a hash map, we store key value pairs. Instead, in sets, we store unique keys or unique elements to be checked in the future. Now, suppose if I encounter a particular character which is already present in my set, that means that my current character is a repeated version of it, and that means that I have encountered duplicate characters. Let's see how it can be applied. If we start our iteration from index 0, we will add A, B, and C to our set because they were not present earlier and they were not duplicates. Finally, at index 3, when we encounter the character B, you will notice that B was already present in our hash set. That means B is a duplicate character and the substring ABCB is invalid because duplicate characters exist in it. So for that reason, we would need to terminate the loop at index 3 and the substring till that point would be my valid substring, which would be substring ABC. Now let's apply this logic for every individual index, starting from index 0. At index 0, we will add A, B, and C to our hash set. And at index 3, when we encounter the character B again, you will notice that it was already present in the set. That means we need to stop the iteration as duplicate characters have been found. So, for index 0, the longest possible valid substring is ABC with a length of 3 units. Now, going to the next index. At index 1, we will add B and C to our set. And similarly, when we encounter B once again, it is a duplicate character, so we stop the iteration. The longest possible valid substring for index 1 would be BC with a length of 2 units. Now when you keep on performing the same procedure for the remaining indices, you are greeted with the following matrix. Finally, we will check the length of each individual substring and you will note that the substring at index 2 CBDA has a maximum length of 4 units and hence that is our final answer. This entire operation takes big O of n square time complexity and for each index we are checking the longest possible substring leading to 2 nested loops. Whereas the space complexity is just big O of n because we are storing a maximum of n characters of the string s. But due to the inefficiency of the previous approach, we are greeted with the time limit exceeded error on this alien-like test case. Hence, there is a need to improve our approach further. There are multiple ways in which we can improve the efficiency of the previous algorithm. We can either take a sliding window approach in combination with hash map, or use pointers in combination with hash sets, or take a completely different approach by creating a memory of characters. Since all of these algorithms have almost similar performance metrics, let's go ahead with the one we are familiar with. Since in the brute force version we already studied about sets, let's go ahead with the second approach. Here is a particular scenario in this given test case. Let's consider ABCB as our substring. You will notice that ABCB is an invalid substring because the character B occurs twice in it. B is a duplicate character. Okay, if I ignore this fact and keep on going forward, you will notice that no matter how farther you go, you will be still having invalid substrings. The reason is that earlier during your traversal, you had already encountered duplicate characters and they cannot be removed, hence your future substrings are also invalid. Okay, if I cannot go further, then how about I resolve the issue? If I somehow manage to remove one instance of my duplicate character, then what will happen? Let's check it out. Here in this case, let me remove the oldest instance of my duplicate character, b at index 1. When I remove this, you will notice that my remaining substring from index 2 onwards becomes valid now. The reason is that there is no more duplicate characters present in it. So, in other words, I can say that if I have two duplicate characters, then by removing the first instance of that duplicate character, I can then go forward in the future to check for more valid substrings. Okay, but there is a caveat to this. I cannot simply yoink this B from index 1. That is because we are keeping track of substrings. Substrings are continuous in nature. They cannot be just partitioned in the middle to break them apart and create new substrings. So, to remove B from index 1, I would need to remove all the elements that occur before it. In this case, since we were starting from index 0, I would need to remove first A, then I will remove B to then result in my final substring which is valid. Now once that is cleared, let's generalize some things. Let us represent the substring, our valid substring, by two pointers, which are L and R. L represents the start of my substring and R represents the end of my substring. The total length of my substring would be R minus L plus 1. You can do the math by checking the upper indices. Initially, at the start of our traversal, L and R both will be at the index 0 because we have not begun our traversal yet. Once that is set, how will we check if duplicate characters are present in our substring? We will simply use the same principle we have did before, that is using a hash set. And with that, we will also keep track of the maximum length of the substring. Let's go one step at a time. At index 0, our first character will be A. Left and right pointers still remain at index 0 and we add A to our hash set. Alright, our maximum length gets updated to 1 because A is a valid substring. Now going to the next index, we will expand using our rightmost boundary. Notice earlier that R denoted the end of our substring. That's why we are expanding using R and not L. L is the beginning. Okay, at index 1, we have encountered the character B. B is not present in our set earlier, so we simply add B to our hash set. And we update the max length of our substring to 2, which is AB. AB is my current maximum valid possible substring. Too many words in a single sentence. Okay, going to the next index. At index 2, we encounter C. As C was not present in the set, we simply add it. And we also update the maximum length. Now ABC becomes my maximum possible valid substring. Now here is the neat part. At index 3, you will notice that we have encountered the character B. Character B was already present in the hash set. So we will not add B in the hash set now. What we will do now is that we will remove the oldest occurrence of my character, which is B. What was the oldest occurrence of B? It was present at index 1. To remove the B at index 1, I need to remove all the elements up till that point. So what will I do? I will remove A from my set. I will increment my left pointer to ignore A. Is the current repeating element B removed from my set? No, it is still not. It is still present in the set. So I will remove the character at the lth index, which is B. Now that I have removed B and moved forward, B is no more present in my set. So that means I have successfully removed the oldest occurrence of my current duplicate character. And that would also mean that the remaining substring, which is CB, should now become valid. Yes, it is valid because C and B are just one and one single characters. No duplicates are present. And since it became a valid substring, we now add B to our hash set. Now R goes to the fourth index. At fourth index, we encounter the character D. D was not present in the set, so it is a valid substring. CBD is a valid substring of length 3. And finally, R reaches the end of the entire S string. The entire substring CBDE is valid because none of their instances are present in the hash set earlier on. And so we update our max length to 4. Here, since R has reached the end of the string, we simply stop our entire iteration. And whatever the maximum length that we achieved during the entire traversal is our final answer. In this case, you can see that CBDE is our final longest valid substring without any duplicate characters with a length of 4. This entire operation takes just big O of n time complexity. The reason being that we are running a single traversal on every single index, and the operation of finding duplicate characters and removing duplicate characters does not exceed the overall n threshold. And the space complexity of this entire operation is also big O of n because we are storing at max n elements in our hash set. We will first initialize our hash set. Let us call it previous, denoting the previous characters that were encountered. Then we will also initialize the left and right pointers. Initially, they were at the 0th index, hence both are 0 and 0. With that, we will also initialize the maximum possible length of our valid substring. Initially, it is also 0 because no substring has been found. Then, we will run a loop of the right index in the range 0 to length s. This is because we will be moving the right pointer, which is the end of our substring, from the start to the end of the position. And when it reaches the end, we will simply stop our entire iteration. Now, my current character would be the character at the rightmost index. And I will check if this character is present in my previous hash set. If this character is present in previous, that means that the current character is a duplicate character. And I will need to remove the oldest instance of this duplicate character. How will I do it? I will run a while loop till my original duplicate character is still in the hash set. That means till the time duplicate character is present in the hash set, I will keep on removing the leftmost occurrences or the leftmost characters. Here, S left is the leftmost character present at the left pointer, and I will remove it from my hash set. And simply once it is removed, I will increment my left pointer to shrink the window. Now, what if this character was not present in the hash set? That means that the current character, my character at the right pointer, is not a duplicate, and so my current substring is valid. So I will simply update my maximum possible length by taking the max between old length and the new length. The new length is simply right minus left plus 1. Great. Now do not forget the important thing. The important thing which remains after all of this is that you need to add the current element to the hash set for future use. By doing this, we can keep track of all the duplicate elements at every single index. Simply after that, we return the total maximum length possible. You will notice that it gets accepted in just 39 milliseconds. But more importantly, we are able to reduce that overall time complexity from big O of n square in brute force to just big O of n, which is linear in nature. Hence, there is a great optimization in the overall performance. That's it for this video guys. Thank you so much for watching and I will see you in the next one.